Okay, good morning everyone. Welcome to Recitation 4 for 11785. Today we will be discussing about a new tool TensorBoard and see how we can use TensorBoard to visualize our networks. We'll also be discussing some of the techniques to see how we can understand data and how we can visualize data to pre-process this better. So before we go what exactly that is, I assume that everyone has installed TensorBoard. We made a post on Piazza yesterday regarding the same, regarding how to install it. If you're using Conda, just make sure that you are installing TensorFlow in it, and it automatically installs TensorBoard with it. If you're not using Conda, you can use pip to install TensorBoard, but that you need to make sure that you also have TensorFlow installed in it. So you can install both TensorFlow and TensorBoard, and you should be good. We'll be going to the recitation notebook as well today, so make sure that you have the notebook and you can go to this link and get the notebook from there. And have it downloaded so you can see, because we'll be running the cells, we'll be going through each cell, and then we'll see how it's actually logging the values in TensorBoard, and it requires you to run the Jupyter notebook locally as well. So make sure that you download it and not just see it. Okay, so why exactly is visualization important? I'm assuming everyone has started with at least homework 1, part 2, and we know that to evaluate a particular deep neural network, loss is not just a metric that we should be looking at, because there are tons of other things as well involved in a network. How your gradients are being calculated, how much you are multiplying it with your, how much does it get multiplied with the activation functions, and how much you are backpropagating, and so on and so forth. And this is something that you really need to visualize and see. And before making any changes to the network, for example, how much should I change my learning rate? How many layers should I have in my neural network? How many neurons should I have in each of the layers? It is important that you know what the consequence of doing that would be. How changing learning rate would affect the gradients, or how exactly your gradients are being calculated right now. And if you clip it by a particular value, what exactly is going to be the change in the network. So it's important that you know and you are able to answer these questions before you're able to answer these questions at least when you're running your models. So it basically tells you, and basically answer the questions for what exactly am I learning through the network. And loss is, of course, just one metric of it, but also tells you other things. So one thing that it helps you with is you can plot matrices with it. Now, you know that every weight matrix that we have in a network, every weight that we have in a network is a matrix, and the gradients that we calculate also is a matrix. So we can plot the matrices and see what exactly are the values in the matrices. So what exactly are the gradients that we are calculating for each layer that we have. And this would help us to answer the question that will adding additional layers in my network will give me any significant results, because now we know, and because we can see how my gradients are being calculated for each layer, I would know that whether my gradients being calculated are similar or not. Because if they're similar, it basically means that you are going to add layers in your network, and with that you are going to add redundancy in your network, which is going to increase the training time of your network, but wouldn't necessarily give you an increase in the accuracy if it's a classification task. So it lets you answer the question that whether adding an extra layer is going to help you or not. Also, it also helps you to do trial and error things. For example, you can add extra layer and see if the gradients are different for it or not, if the weight matrices are different for it or not, and possibly also see if my loss values are being decreased or not. As we are going to see in the later homeworks as well, that we'll be using recurrent networks for our homeworks. Also, the data set that we have for homework 1 part 2 has a temporal associativity. So that same data set can also be fed for a different task, of course, can also be fed to a recurrent network to make better classifications. We'll be discussing about the task later on, but we can be, for any data set or for any task which has temporal associativity with it, we can use recurrent networks for it. And using recurrent networks brings in the problem of exploding gradients and vanishing gradients. So we generally have to clip our gradients to a particular value to make sure it does not just blows up. So if you're able to see the gradients, we'll know what exactly should be the value for us to clip it with, and we just won't be using any random scalar to clip our gradients with, because that can definitely lead to a slower convergence, and therefore it'll take a lot of time for you to achieve better accuracies. Of course, the question of when to stop training, as we discussed in the last recitation as well, early stopping is one thing that we should be using to evaluate how exactly my model is performing on the train and the validation set. So it is possible that we did see a lot of people running their models for 100 or maybe even more than 100 epochs for homework 1 part 2, which is definitely not the case because you won't be running your network for that many epochs, and you should be getting a much better accuracy before that. So it would be really beneficial for you all to see how your train loss is decreasing, and at the same time how your validation loss is increasing or decreasing as well. And you would want to stop your network training as when you see that your validation loss increases after a particular time, after a particular epoch in training. Also, something that we discussed last time while we were discussing about different tuning methods was how we can initialize weights. And today we're going to see how exactly weight initialization why exactly it plays a very important role. As we discussed last recitation, if we are initializing our weights to 0, we know that we are multiplying anything with 0 and then adding it with zeros, and it's all just zeros. And when we are backpropagating, our gradients also do not get a good value for us. And the values that we get from backpropagation do not make sense. And we'll just see why is that the case. Also, you can see how different your activation functions are for the data set and for the task that you're evaluating. Again, something that we'll go through in the notebook. Different tricks like batch normalization, dropout, what they're doing to the network, are they making sense? Are they affecting my network too much? These questions we'll be able to answer. In general, it helps you fine-tune the performance of the model that you have already created. Also, it tells you whether you need to add something in your model or remove something from your model as well. So what TensorBoard does, for evaluating, what we have been doing right now is just plotting a scalar value of loss and seeing if the loss is decreasing or not. But you can think of TensorBoard as a visual logger. We don't have to log these values anymore. We don't have to write print statements or have a logger set up to log these in a particular text file and go through the text file and see. We can just log all the values in TensorBoard, and TensorBoard is automatically going to plot all these values for us, which will make it easy for us to visualize visualize different things. It helps you, of course, understand, debug, and optimize the neural network that you have. And one of the most important APIs that we have for TensorBoard is tf.summary API. Now, tf.summary API is a public API that TensorFlow, that was originally designed for TensorFlow, but later adapted for other frameworks as well, like PyTorch. And what it lets you do is it lets you log all the operands of your graph. Now, whenever we say that, we know that when we are making a neural network, when we are making a deep neural network, we are basically making a graph, and we are basically making a data flow graph. And in that data flow graph, we have the operands, and we need to plot those operands to see how the values are. So when I'm saying that we need to log the operands, we basically log all the weight matrices, all the losses, and all the other values that we have. Now, using TensorBoard, you can log scalar values, you can log matrices as well, two-dimensional matrices as well. But how exactly are we going to visualize a particular matrix? If you're just plotting the matrix value itself, doesn't make any sense to us, because then again we'll have the same problem of logging versus visualizing. So what TensorBoard does for you is it visualizes a particular matrix using histograms, and we'll see how exactly it does that. Along with scalars, along with two-dimensional, so scalars are one-dimensional, two-dimensional weight matrices are, we can plot it using histograms. You can also plot images through it. So think of, when I say that we can plot images, I basically mean that, again, it's going to be a matrix. It's going to be two-dimensional. It can also be three-dimensional, where the third dimension could be the number of channels that you have in that image. And the TensorBoard automatically plots that image for you. So you can think of confusion matrix as an image, because that's a two-dimensional matrix, and then you have values between, and you can have values from 0 to infinite, depends on the number of samples that you have. But you don't have to worry about how exactly I'm going to normalize those values in my confusion matrix. You can directly just create a confusion matrix and send it to TensorBoard to plot, and it's going to plot all the values for you. And we'll see how it does that. Along with confusion matrix being a type of image, we'll be using convolutional neural nets as well. In the next weekend's one, we'll get to know more about what convolutional neural networks are, what filters are, and what other things involved in the network are. And when we do that, we know that we'll be having different parameters. We'll be having filters which basically extract the information out of a particular data that we have. It could be image, could be speech, anything. And then that filter again is a two-dimensional thing, and we can use images to plot the filters and see what features are being extracted by my model. These things are important, and you'll realize soon in the part 2 of the homeworks that we have that you need to understand what your models are learning. So starting with, it also lets you log text values and other stuff. But primarily, we'll be talking about scalars, histograms, and images. So starting with scalars, so we know that a scalar is going to be a one-dimensional array or one-dimensional object. Now, we definitely would have to see how exactly the value of that one-dimensional object is changing with time, because we'll be running our models for different epochs, and we need to see how that value is being decreasing or it's changing with number of epochs. So the way we plot a scalar value is we plot it in a two-dimensional setting, and the second dimension is going to be time for us, and that time would you can say that time is also the number of epochs that you train your model for. So you have in a particular, in a generic neural network training setup, you will have your loss would be something that's scalar. Your prediction accuracy would be something that's scalar. Your learning rate would be something that's scalar. So you can plot all these values using tf.summary.scalars. Now, how exactly are you going to plot your weight matrices? And that's what I meant when I said we are going to plot histograms. So for a one-dimensional scalar, we were plotting it in a two-dimensional setting, right? Because we wanted to have time dimension as in it to see how it's changing with time. So for a two-dimensional for a two-dimensional object, for a two-dimensional matrix, we'll plot it in a three-dimensional setting, where the third dimension is, of course, going to be the time. So this here is an example of us plotting a weight matrix which has been initialized to a mean of 0. It's a normal distribution. The weight matrix has been initialized with a normal distribution. The mean of that normal distribution was 0, and the standard deviation was 1. So we can see, and the normal distribution was 1. Now, the z-axis that we have made here, the z-axis is the time dimension. So if we see farther away in the time dimension, when it's initialized to 0, this value, we can see that the mean here is 0, is centered around 0, and the standard deviation is around 1. And the way that we are plotting it is basically we are with increasing number of epochs, with increasing time, we are shifting the mean. It's basically a running mean, something that we have been doing for a lot of time. The standard deviation for that particular distribution, for that particular weight matrix, is constant. It remains the same, but the mean has been changing throughout, and it's increasing. So we can see as the time is increasing, this particular distribution is changing from 0, and at the end of around at around 400 epochs, the distribution is centered at mean of 5, and it has the same standard deviation. So so here, what these three axes, what exactly are the values in these three dimensions? Z, of course, is the time. X-axis is going to tell you what are the values in your weight matrix, and the Y dimension, how tall your histogram is basically telling you how many values do you have for that particular value. So suppose that you have 100 values for value equals to 5 at time equals to 400. So that's why the height, the Y dimension, is very large at x equals to 5, and the value for y decreases as we move along, because the mean, of course, is 5, and you'll have a lot of values at 5 for this particular distribution. And we'll see how these histograms are. The third thing that we can use TensorBoard to plot are images, of course, and as we discussed that now images, of course, are going to be two-dimensional in the sense that you will have a height and a width for it, but of course it will have the third dimension of channels where you can see different colors in it. And of course you can see how it's changing with time. So you'll always have that time dimension where you can scroll through that and see how the particular image has been changing over the period of your training. So it's a single matrix in an image, and you can plot it. You can plot, of course, CNN filters, kernels with it. You can plot confusion matrix. You can plot a confusion matrix with it. And the tf.summary.image automatically captures automatically does the normalization for you. So you don't have to worry about keeping the values between 0 and 255 to get in particular image, to plot it as an image. It would be any value, and it automatically rescales it to 0 to 255. Now, how exactly can we run TensorBoard on AWS? Because a lot of you are going to use AWS while you will be training your models. So TensorBoard comes pre-installed in the deep learning AMI that you use in the instances that you use on AWS. You just have to activate the environment that you're using. If you're using PyTorch, you use PyTorch underscore P36 for Python version 3.6. If you're using TensorFlow, you activate the same environment, and then that TensorBoard is pre-installed, so you don't have to worry about that. But if you're training on AWS, you'll not be able to see what exactly is happening in the network because you don't have a browser there. So whenever you start TensorBoard to log values in the browser, you will not be able to see it. So it's important that you forward the port on which TensorBoard is running on that particular instance. So TensorBoard by default runs on port 6006. So what you can do when you are SSHing in your particular instance, you can just forward that port using the -l command. And once you do that, once you SSH in and once you start TensorBoard on your AWS machine, it will automatically forward the port, the default port for TensorBoard, and you can then visualize and you can see the entire TensorBoard module in your browser. That's all what I have for slides. Let's shift to Jupyter Notebook and let's see how exactly we are going to do that. And I advise you also, if you guys have the notebook locally, let's do it together. Okay. Okay, so the task that we are going to work on is the same task that we took up in Recitation 2. The task exactly is going to be that you'll have your training data as a set of 2 points. You'll have x1 and x2. They are going to be polar coordinates on an xy dimension. And what you're going to do is you are going to predict whether that particular point that you have, the polar coordinates that you have, they lie within a circle of radius 1 or not. If you want to go more into the details of what exactly was the task 2, I suggest that you go to Recitation 2 and then see it. But that's on hindsight, that was what we wanted to do. So the dimensions that we are going to have for our training data for the x that we have is just going to be 1 cross 2 for a single sample. If we do it in a batch, it's going to be batch size cross 2. And the labels for it is just going to be one dimensional. It's going to be scalar. More specifically, it's going to be binary because it's a binary task. We are trying to predict whether it's inside the circle or not. So it's the same task that we'll be doing. Now, how exactly TensorBoard works is that you make use of the tf.summary API for it, and there is a method for it, a file writer method. And the moment that you type in tf.summary.filewriter and provide in a particular directory to it, a particular path to it, it automatically sets up TensorBoard to look up logging in the particular path that you provided. So for example, what we're doing here is that we are initializing a writer object, and that writer object is the file writer object that we have from the TensorBoard, and we are asking the TensorBoard to log or to look for values that we are going to log in the logs directory that we have. That logs directory is in the same directory as this particular notebook, so that's why it's // and then we have logs. What it does is basically it creates a writer object that can then write events in that directory, and then TensorBoard automatically picks up all the events that you have stored while you are running the program from that directory and plot it for you. We'll be covering how we are going to do that both in TensorFlow and PyTorch, but we'll be starting it with TensorFlow because TensorBoard was primarily designed for it, and it's easier to at least understand what TensorBoard does there. So for people who are doing it in TensorFlow, I don't think I should be saying that, but for people who are doing it in TensorFlow, the assignments in TensorFlow, it's better that you don't follow the Recitation notebook as is, because there are better ways to use TensorBoard as well. And we can talk more about how we can use the hooks for plotting the values and so on and so forth. So let's import all the necessary libraries that we have. And similar to Recitation 2, we have a particular function that is going to generate the polar coordinates for you. Basically, it's going to generate the x and the y for you. So this function is, I'm just going to hold on for a second because I think the values are, is it me who's doing something? No. Okay. Is it good? Oh, okay, cool. So the function, the sample points function is the same from recitation 2, where we are just sampling random points for x and y. We have the labels as well. The labels are binary. And then in this particular third cell, what we are doing is we are generating the data set. So we can see that the shape of our x is 10,000 cross 2. The shape of our y is just 10,000. It's just binary. And we have the total number of samples that we have for this task is 10,000. Now, for logging a particular value in for a particular setting, we just have to change the directory where we are logging the paths for it. So for example, if we want to write all the values for this particular setting of a network, and while we are training it, the path for which we are doing that is just logs and train. So inside logs, I'm again creating a subdirectory named as train, and in that I'm going to log all the events for it. So this example is particularly in TensorFlow. I'll just briefly go through it and explain it what exactly this is. And what we're doing here is that we're just building the graph for the setting. We are going to use the number of layers that we are going to use is going to be 2, and the number of units that we have in each layer is going to be the same. It's going to be 12. It's a very small neural network because the task itself is not that intensive. We have the activation layers initialized. We have the weight initializations and the bias initializations as well. Our x's and y's here are the exact same x's and y's that we have initialized before. It's just a global step to keep track of how many epochs are we running for in the network. And what we do here is for each layer in the number of layers that we have, I just apply a dense layer. A dense layer is a fully connected layer, and it automatically creates the weight matrices for you, initializes it using this kernel initializer that we have, initializes the bias for that layer using the bias initializer that we have, and using the activation function as well. It automatically applies the activation function for you as well. Finally, when we have parsed it to 2 layers, what we want is we want to create logits, and the logits are going to have a dimension of batch size cross number of classes. The number of classes we have in our task is just 2. So that's why the number of units here in our logits is just 2, because it's a binary classification. Then we are calculating loss using softmax cross entropy, and then we are just reducing it on the batch dimension to get the mean of the total loss that we calculated for that particular batch. So this is pretty straightforward. We have the Adam optimizer as well, and then we are using optimizer to minimize the loss we have. Now what we are doing here is, this is something that is really important for TensorBoard. So we are computing the gradients here, and for each gradient that I have computed, I am using tf.summary.histogram, and in that particular method, I first provide the name for that particular matrix, which is just a string, which could be anything, and then finally the value of it. So it's pretty simple. We just provide the name that you want to plot it for, and then you just give it the matrix that you plot. Similarly, for what we're doing here for 2-dimensional, it's pretty similar for 3-dimensional for scalars as well. Here, what we are doing is we are using tf.summary.scalar and plotting the loss, the scalar loss for it, and also we are plotting the accuracy for it. What we are doing here in this particular line is we are collecting all the trained networks, all the parameters that I have. They're all 2-dimensional weight matrices, and then using histogram, I'm just plotting the name of it and the matrix. That's it. And I use tf.summary.merge all to merge all the event files that I have generated yet, to merge it in a single doc and just plot it on TensorBoard. I'm just going to run this cell, and that's it. So that's it. You can use scalar to add scalar values, histogram to plot 2D matrices. And now what this particular function is going to do is it's going to run your neural network for a default setting of 100, and then what we are doing here is we are just running the value, getting something out. We are getting the summary op that we had out of the graph. We are adding it in the main file writer object that we created. So here what we are doing is train writer underscore tf is the file writer that we initialized before. We're just adding the summary, and we're adding the time step at which we're adding summary. So it's going to be the number of epochs, and we just use the file writer.flush method to flush it to the TensorBoard. So let's see. Now what we're doing right now is I'm initializing the weights for my network from pretty close to 0. So it's going to be from minus 0.01 to a max value of 0.01. My biases have not been initialized, so they're going to be 0. They're important because we'll see, because we can see that they'll be initialized to 0 initially. And then let's start. So we started training, and it has now created all the required event files in the directory. So I'll just briefly go to this. So this is going to be the directory in which I'm running currently my Jupyter notebook, and it's the same directory in which I'm logging as well. So we can see that we have a logs folder here, and in that logs folder, my file writer object was creating a subdirectory of train. So we have that, and in that I have an events file generated. Now TensorBoard is just going to pick all the values that we have outputted in this events file and plot it, and that's it. So I'm just going to zoom it in a little. We are going to go in the same directory that we have been going. So it's the same directory that we have. You can see that we have the TensorBoard IPython notebook and the logs directory. Now what I'm going to do is I'm just going to call in TensorBoard with a log, with a particular argument which is going to be log dir, which tells where the log directory is. It is nothing but it's logs for us, and that's it. And let's start. So TensorBoard automatically starts itself on, it'll start on the default port of 6006, so we need to go check our local host 6006. And we can see that we have our, yeah, sorry.
Sorry, what was the command to launch TensorBoard? I missed it.
So what you are going to do, let me do it again so that you can, follow it. So you'll be typing TensorBoard, and while you type TensorBoard, you have to follow it with a particular argument. That argument is going to be log dir. It's going to be the log directory. Is it visible? So we have TensorBoard, we have the log directory, we're passing in an argument there, and that equals to the logs that we initialize the file writer object with, right? Let's start it. So we have started it, and we can see it automatically starts up at 6006, the default port. So we can go on localhost and see this particular port. Okay, so important stuff first. The three values that you're seeing on top, the scalars, the distributions, the histograms, they are basically what we have discussed so far. Scalars, histograms are histograms. Distribution is also a way of plotting histograms. We'll see what exactly is the difference between distributions and histograms. For images, if you are plotting images, another tab here will come and it'll be named as images, and you can click on it to see how the values are. So let's first see. So we did decently. Our accuracy did increase, but it only increased after 120 epochs, which is primarily due to the fact that we initialize our weight very improperly, initialize it close to 0, which is not good, which we have been focusing on for some lectures and some recitations now. So, and we can see why. Even though our loss is decreasing till 120 epochs, and we can see that it started with, it started with a value of 0.89, and till 120 epochs, it did reach a value of 0.7. But the accuracy during this did not even move. It was 0.52, and it remained 0.5. So if you were just logging in losses, you would see that your loss is decreasing, and you would expect your network to really learn in the first 10, 20, maybe even 30, and now you've run it for 100 epochs. You would definitely want something out of the network. But the accuracy wouldn't really improve because your gradients will not make any sense. And let's see what your gradients are looking like. So that's your loss. It's your accuracy. Let's first look at the histograms, and then we'll be looking at the distributions. So what we're doing here is for each layer, we are plotting in the biases, and bias 0 is going to be the bias that we have, the bias vector that we have for that particular layer. Kernel is the weight matrix that we have. As we can see, this dimension is a time dimension, as we discussed. Now, it was initialized improperly, and it was initialized close to 0. We can see that the maximum values are 0.5 and minus 0.5. And even after running for 200 epochs, the values haven't really changed that much. It has remained pretty much the same. There is some hope, at least for the weight matrix that we have. We can see that these values are increasing a little, but there are certain values that are diverging as well from zeros, and that's good because we wanted that. We wanted it to be diverged enough so that we are able to learn something. So we can see that it's really reaching there, but we are wasting a lot of time just by initializing it to 0. Same goes for the second kernel, and we can see all of them are just zeros. Some of them did diverge, and they are possibly the values that were giving you the decrement in the loss that you were seeing, but you're not really learning anything because more than 80% of your network is just zeros. The neurons are not firing, you're not getting any values for it. Same goes for bias as well. So these were for the two layers that I had. This is for the last layer that I had, the logits in which I'm creating the logits. These are the gradients that I'm plotting, and you can see pretty much that the gradients are itself 0 because you initialize them to 0 for all the biases and the weight matrices. They're at zeros. They're not exactly centered at 0. We can see it's centered at 6.99, but they're not changing that much. And there are some values that did change, but not really giving us a good score. And similarly, for all the different things we have, we can see all the different weight matrices. Great. Now what we are going to do is let's change this initialization. What we are going to do, I'm going to use Glorot initialization, which is pretty similar to Xavier initialization that we discussed last time. We are going to use that to initialize our weight matrices. It initializes it using the same formula that we had, 2 underscore that number of inputs, outputs, and the square root of it. And the bias initializer is going to be from values of -0.2 to 0.2. Sorry, I did not go through. So these are the histograms that we have. What exactly is distributions? So distributions is just a way for you to know what is the maximum and the minimum value in your particular weight matrix right now. So you could see that initially at epoch 0, I initialized my weight. I did initialize my weight. So I'm seeing this wide divergence here. But for the kernel weights, you can see I initialized it pretty close to 0. It was 0.01 to -0.01 to 0.01. So initially, they're all just zeros, the maximum and the minimum values. And for the first 40 epochs, they're not even changing. And at around 60 epochs, they change to something like 0.1 and -0.1, and then they keep on diverging. So it would have been really, really beneficial for us to initialize these values from in the range of, let's suppose, 0.3 to -0.3, and start the training from there. And because in that case, we wouldn't have really spent 120 epochs or even 200 epochs learning nothing. Similarly, we can see that this kernel weight has been initialized pretty close to 0, and only when we run it for a lot number of epochs, we can see the maximum and the minimum value diverging enough. And so for the gradients, even the gradients that we have. So for 60 epochs, the gradient for my first matrix was just 0, not learning anything. So what I'm doing here is I'm initializing it with Glorot biases. Let's see how it does. So now the only difference that I have here, everything is same, except the file writer object that I had. The file writer object, now I have changed it to log values in train underscore init. And when I ran that, and when I'm going to refresh this, I'm going to see the train underscore init graph as well. Now I can see, and I can, so let's start with scalars again, like we did last time. So now we can see and we can plot how exactly these two different things have worked for the 200 epochs. Great. Initially, the loss, the accuracy for our model for both these initialization was 0.5. Makes sense because we were just randomly guessing. It's a binary classification, randomly guessing, not learning anything. Accuracy is 0.5. But with increasing number of epochs, with our initialized, this value has definitely increased a lot. It has reached to an accuracy of 0.94 in 200 epochs, as opposed to 0.58 for the previous initialization. And so has our loss as well. So the loss that we have is also lower for better initialized graph. Let's see the histograms. Now, we can see a lot of divergence here, which totally makes sense. A lot of divergence means good. It means that we have biases and weights spread out throughout the network. Similarly, we can see how we have initialized it closer to 0, and it's not really changing. But now with Glorot initialization, it's spread out throughout the range of under square root of 6, and using that formula, it's spread out throughout that uniformly. And it helps the network to diverge enough, get proper gradients as well. Same goes for my bias, same goes for this final kernel as well. Initialize it properly. A good divergence generally means a good calculation. Let's see the next page. Let's see how our gradients are performing as well. So even I can see that I have my gradients as well spread out. And you can see the values at which they're spread out. They're spread out to a very large values. They're not between 0 and 1. They're not between 0 and 10. They're spread out very large value. And we'll just see in the next example, when we have different activation functions as well, how these values can be really, really large, which causes the problem of exploding gradients, and you need to clip those values. And using these graphs, you can get a better idea of what that clipping value should be, what the clipping scalar should be that we discussed last time in the last recitation. Similarly, for these gradients, we're seeing a decently enough distribution. Not so much in this because it's the second layer, and it's the second layer for our weights, and so on and so forth. Right. Now, different activation functions. So this was different initialization techniques, and you can see how they are performing. Now, different activation functions. So some of the most common ones are sigmoid, tanh, ReLU. that we have asked as well for you to implement it in homework on part 1. But let's see what the pros and cons are for the activation functions and we'll see how they perform. So for sigmoid, we have the formula of 1 upon 1 plus e power minus x. And that basically means that the values that you will be having for any value of x will be between 0 and 1, right? The function for the sigmoid starts from pretty close to 0 and goes to a value of 1 for positive values. It's pretty close to 0 for a value of minus infinity. So the values are pretty squashed up in that range of 0 to 1, in that y range of 0 to 1. And that's one of the biggest problem of the sigmoid layer. It easily saturates or easily dies off. When I say it easily saturates, I mean that when I'm multiplying something x w plus b and if that value is large enough, then if I apply sigmoid to it, then the values are going to be pretty close to 1. So they have saturated. So for a particular value of x if my x could be, wx plus b could be something like 500, wx plus b could be something like 50,000. But because we are using sigmoid, the values are going to saturate. Similarly for negative values as well. So the problem of sigmoid is that it saturates. And that is a problem which is pretty common for tan h as well. The values will not be from 0 to 1, it will be from minus 1 to 1. They'll be centered around 0. But still, you have that range of minus 1 to 1 where your final output is going to be after you apply the activation functions. And that's why the convergence also is a little slow in these networks, because you're not allowing your gradients to vary that much. You're keeping them in a particular fixed range. For ReLU, that's not the case, right? Because it's not a squashing activation function. It's much like a threshold activation function. If it's less than 0, I don't care. It's all 0. If it's greater than 0, just keep the value. Let's see how it goes. So that's why it converges quickly, because you're not squashing. You're not making your gradients to go in that particular range. But the problem with ReLU is that let's suppose that you're passing something in your network and you made a huge update to the weights. Now, if you're changing your weights too much, if there's a big gradient that you have updated your weights with, it is possible that your weights are now negative. Now, for any positive or negative input that you have that you are going to feed, the product of wx plus b it is possible that that product wx plus b would always be 0. And now because you're applying ReLU, that particular neuron is never going to fire at all, because the values will always be 0. Why? Because you had a gradient update that changed the weight and the bias vector to a very large negative value. So now you have that problem of dying of a dying neuron, and that's very, very common in ReLU. So one common way to avoid that is to keep your learning rate a little lower for ReLU, because if you have a high learning rate, you're directly multiplying your gradients while you're back propagating, and that could potentially lead to you updating your weight matrix wrong. And that's why to counter this specific problem of ReLUs, we have leaky ReLUs as well. And what leaky ReLUs does is, for all the values less than 0, it does not just keep it to 0. It gives a very small negative value for it. It's like something like 0.001 or 0.01. And that makes sure that your neurons never die off. Something for you guys to try out is to see how the Xavier and the He initialization works on all the 3 different activation functions, and you'll get to know why we're doing that. Let's plot. I'm using the different activation function for all these different networks. It's going to be sigmoid, tan h, and ReLU. I'm just going to run this, and I'm going to see how exactly are my values changing for all these different things. So let's start with scalars first. I don't want to. I don't want to see this. Don't want to see gradient as well. Just want to see sigmoid, tan h, and ReLU. Great. As expected, the problem with sigmoid is that it is squashing your gradients, not giving you a great accuracy. Leaky ReLU is really performing well, even better than tan h, as expected, and so are the loss values as well. So we can see that for sigmoid, it's not really performing that well. Leaky it is. Loss as well for leaky ReLU is much lower than the loss that we are getting for sigmoid and tan h. You can go through the histograms as well. Yeah, sorry.
Not a question about this specifically, but more in general.
Mm-hmm.
I've heard before, and this seems to verify, that tan h is just kind of like a strictly better version of sigmoid.
Yeah.
So why use sigmoid ever?
You don't actually.
Okay.
You don't ever use in sigmoid used to be a great activation function. People did use it, but after ReLU after ReLU and different versions of ReLU, sigmoid really just died off.
Okay.
you don't really use sigmoid. You can never use sigmoid. Maybe you can use something like tanh, but always go with ReLU or leggy ReLUs. For a lot of tasks, they're pretty generic. And you can see how your network is being distributed for the values as well. I just wanted to see, because I've been talking about the gradients for sigmoid and that stuff, and just want to see the gradients, and we can see the gradients for the sigmoids are just squashed up. They're not learning anything, which goes with what we have been discussing for a long time now. So you can see how the distributions are, how the histograms are changing, and what the maximum values are, and see how they're performing. Finally, we want to plot images as well. What we can do is you can use the tf.summary.image to plot a particular image, and the input to that has to be just a weight matrix. That's it. You don't have to worry about anything. Pretty similar to what we have been doing for histograms and scalars. And now what we're plotting here is the confusion matrix. So I'm going to create this new graph, and I'm just going to start training it for like 50 epochs and see how my images are being plotted. So if I refresh this TensorBoard, I can see now that I have an images tab, and I can see this is my confusion matrix now. I can scroll over this from first step. So what exactly is my first step? What exactly are these values? So so in a 0 to 255 scale, 0 is black and 255 is white. So we want our confusion matrix to be all white in the diagonals, right? Because we want higher values to be on the diagonal and lower values on the non-diagonals. So initially, that's not really the case. You still have values. You still have values that are not present here, but that are present here and here. So, and with increasing number of steps, step here is the epochs that you have. With increasing number, you can see how your confusion matrix is changing. And finally, it does get better, not really, but if you run it for more epochs, you can see how it gets better. And it is something that you can just plot and see how your confusion matrix is also changing. And you can see for which particular class you're performing better, which particular class you're not performing better. If it's MNIST data, you can see why exactly 7 and 9 so closer, and why my network is not properly predicting 7 and 9 or so on and so forth. And you can see that with confusion matrix. Also, when we are plotting these values, we can also plot, like what we're doing here is we are plotting it for train. You can also plot it for validation, and you can plot it in the same graph. And then you can see that your training and validation loss should decrease initially. And the moment your validation loss starts to increase, you can stop that. And that's how you can easily implement early stopping. Finally, for a lot of people, how exactly we're going to use in TensorBoard. So the problem is plotting in PyTorch is a little different, because you'll not be using the tf.summary method, the public API itself, because it's primarily made for static computational frameworks like TensorFlow, Keras, and Theano. But for PyTorch, you can use the tf.summary class itself and log the values. So what we are giving you here is a logger class, which you can directly just use and plot your values in the network with. And we can see that in here, we have this self.writer as the same file writer object that we have been initializing with a particular log directory. And instead of using tf.summary with a small s and then adding histograms to it, what we are doing is we are using the main class of summary, and then we are using it to plot a particular value where I have a particular tag as my scalar value, a tag as a string, and simple value is just a value. This particular function in this logger class is the log scalar is the log scalar method. The tag is the string, value is the exact value of the scalar, and step is the number of epochs that I have it for. And similarly, I won't go into the details of how exactly we are plotting histogram. What we are doing is basically we are creating the tensors to NumPy objects, and then using that NumPy objects to plot it in TensorBoard, because that's what you have to do when you are using TensorBoard for it. But this is a function that lets you plot a histogram. We have shared a particular GitHub gist here as well. You can go through this gist, and this gist, we have taken this particular snippet from this gist itself. And in this particular logger class, you'll also get the method to plot images. You can just use that and plot the images as well. We have not taken that snippet here, and just use it. And finally, this is something which is exact similar to what we did in Recitation 2. Initialized our model with linear, ReLU linear. We have created two logger objects here, the training logger, the validation logger, and finally, this is the same training routine, exactly same. Instead of printing values that we were doing in Recitation 2, if I mod 100 equals to 0, what we are doing is we are using the training logger to log scalars and log histograms. That's it. You just have, and you can get all your named parameters, all the gradients that you have using the network.named parameters. You'll get the values, just plot them directly using the logger class that we have given you. You have initialized it, and then you are going to run this. Sorry. Let's refresh it, and we can see this is the train PyTorch thing here. The network is different. That's why the accuracy is a little different. Let's just see this. So this is something that we are plotting for PyTorch. It's pretty similar. The concept is just similar. What you're plotting is similar. In the histograms as well, you can see the plots for your what you've trained in PyTorch, and you can see your biases, your gradients that you're calculating, and so on and so forth. It looks pretty different because the network is different. And that's it. So yeah, that's it for TensorBoard. And now Nihar is going to explain the different techniques that we can use to visualize data. Sorry. Yeah, totally forgot.
Yeah, there are two cables. I'm not confused.
HDMI 1 only comes to the webcast.
Yeah, I think this is it. Yep.
Hey, there we go.
Okay, hi. So firstly, is there anything wrong with this side? It's such a non-uniform distribution. Yeah, so, okay, get it. So anyways, you've been training data, you've been training on MNIST, you've been training on the speech dataset. So when you think about it, an MNIST image has what, 784 dimensions. So do you actually need so many dimensions to classify something? Humans, when we look at something, for example, this here, we kind of live in a 3-dimensional space. So we don't exactly need to know 784 values to understand that this is a chair. So why do you think the network would need it? Do you think the network would need 784 dimensions to say that a digit, an image is corresponds to a digit, which is 1 or 2 or 3? You don't need it, right? So basically, we are just wasting a lot of space. We don't need so many independent or dependent variables to tell that something corresponds to something. So basically, what the lecture right now is going to talk about is dimensionality reduction. That you don't exactly need so many pixels. So how do you reduce the number of pixels to get to a much smaller number of variables that represent the data? So let's look at some nice example. Let's look at this pig. So this is an adversarial example. So this pig, as it is, if you run it through any latest model, which is a VGG or any model, it will tell you that it's a pig. But just changing a few pixels in it, just add some noise. This is not a dumb way of adding it, but it's an adversarial way wherein you actually trained the network to cheat the model, right? So just add some noise, smart noise, the network is wrong, completely wrong. So why do you think it is happening? As a human, you cannot say the difference between this and this image, right? So why do you think that's happening? Come on, take a guess, guys. Yeah.
Higher dimensionality.
Okay, higher dimensionality, definitely, but why exactly?
close values. So when you added the noise, it shifted the pig across the pig boundary to the boundary.
So that is what happened here. Like you added the values in such a way that you cheated the network. So the reason that this is happening is basically because there are so many values inside this image that are not actually helping the network in classifying it as a pig. There are so many extra values there. So you basically just change pixels in such a way that those pixels tell the network that it is an airline. But as humans, we can't really cheat it. So this is also a very big problem in current scenarios wherein you can just print these pictures, take it in front of an autonomous driving car, whatever it is, and the car understands what the image is. So it is a huge problem. So big companies basically spend a lot of time so that their models are not prone to such problems. So how can you reduce the dimensionality of an image? Like it is established that you don't need all of those pixels to get there. So firstly, let's talk about mathematical methods, how people used to do this before. There are two ways, linear models and nonlinear models. Yeah. And yeah, so linear models are basically a linear combination of all of those pixels, or some small subset of those pixels which actually represent the entire image. And then nonlinear models like the t-SNE they are based on some probability distributions. We'll look into that. And also there is a huge branch of machine learning called the unsupervised learning, wherein you just give the image and the label, and the network learns to reduce 500 cross 500 pixel image into a single class label. So that is dimensionality reduction, right? You're taking 500 cross 500 pixels and then getting it down into one single label, one hot representation. You get it? So in fact, you have also been doing some sorts of dimensionality reduction, wherein you send in 784 pixels of an MNIST image into a neural network and get out a one hot representation. It is also sort of a dimensionality reduction. It is just using a neural network. And lastly, we'll be concluding this by the ZCA, which you will be implementing in the next class. It is not a dimensionality reduction method, but it is a way in which you can highlight those features in an image that actually correspond to, that actually help the network focus on the important regions that give you the output. So you don't have to deal with the noise in it. So let's start with t-SNE. t-SNE is a t-distributed stochastic neighbor embedding. So basically what happens is, so this is a very slow method. So can you see it? Can you guys see it? Yeah. So basically we have these samples in some space. So what t-SNE does is it picks one sample, compares this sample with every other sample in your data set. And then it projects it in a form of a normal distribution, basically. So you have this distribution. So suppose you're starting with this sample. The sample is here. And then you calculate the distance with the sample. Probably, because this sample is very close to this, it is plotted here. And then this guy is plotted somewhere here. And since this one is very far away, that comes towards the edge of the distribution. Right. Yeah. So basically, this is your initial distribution, and this is how you're trying to cluster it. So you can see this as a two-dimensional representation that you're reducing it into a single-dimensional representation. So this is a really nice method. You can get some really cool results with this. Keep doing this for all of these samples. It runs iteratively. So you have to compare every single sample with every other sample inside your data set. So as you can see, it might be really computationally expensive. So this is not really preferred. You'll also see how long it takes to probably cluster 10,000 samples in a while. So you have to keep doing this for all of them. Another problem here is the distances are not going to be the same for each cluster. So you ideally would want to have these three. So you'll have to normalize each of these normal distributions and then put it on another dimension. Yeah. So finally, once you're done with this, once you have your similarity scores between each of these samples, you plot it as a matrix. So this matrix basically represents the distance between the samples. Obviously, the diagonal is going to be the distance with respect to itself, so that is a 0. So every other sample, you can see that this is how the clusters are forming. The blues become one cluster, the reds become one cluster, and the yellows becomes another cluster. So yeah, so basically, in this sample, you have reduced 3-dimensional data into 2-dimensional data. And this applies for all. It doesn't really matter how many dimensions you have, as long as you keep comparing it. But since you can see, it is very slow. So we'll be going through the Python notebook. Did you guys download it from GitHub? So we'll get there in a while. So we'll be using the MNIST dataset to see how we can cluster these data. So the next one is a linear model where you use some linear combination of the variables that you have to reduce the dimensions. For example, let's do this. So you see, you have the same 3-dimensional space. You have some samples plotted here. And then what you do is so this is a bit cool. So you'll probably be implementing some normalization in your next homework. So this might also be helpful for that. So this is your distribution initially. So basically, everything about PCA is you're trying to fit a line in between these samples. You try to fit a line in such a way that the variance is very high. I mean, you select those dimensions that add the highest variance to the data. And then you can also look at it in this way, that you're trying to minimize the distance between the samples and the line that is being drawn in between them. So firstly, you zero mean it. That is, you shift the mean like we discussed in the previous lecture. You just take the average of all of these points and you draw a line. This is the mean. And now what you're trying to do is you have to fit a line in between this. You fit a line in such a way that the distances are the least and you have the highest variance. You can understand this as the samples are very nicely distributed. It's the highest distribution that you can have on that line. So that is what is being shown here once you have that distribution. So the higher dimensional data that you have can be put on a line and can be shown as you're reducing the dimensions. Any questions until now? Yeah, so you can basically only do this for data sets that have really high correlation. That is, if you have a if your data has high correlations, you can turn off some pixels that are not adding real value, right? If you're using 5 pixels to show the exact same value, you don't need 5 pixels. You can remove the 4 and you can just use 1. So that is how this works. So let's move over to the Jupyter notebook. So, yeah. Yeah. Firstly, have you guys installed pandas, and do you have NumPy with you right now? Okay. So, anyways, if you don't have the MNIST dataset, you can just download it from the link that I've given. So, the first step is just importing NumPy, import pandas, and then you have to just read the MNIST values, load it in the step here, and then you separate out the labels and the features. So basically, you'll be running PCA and the tsne on the features and not on the labels. You don't really have to worry about labels now, because you are trying to cluster the data without actually knowing the labels. So you can use it as a comparison matrix after all of this is done, but right now you don't have to look into it. And then in this step, it is basically helping you to better plot the data. A data frame is basically one of the container objects that helps you put images into it and represent it in a tabular form. So this is what we have. You have selected 30 random samples from the MNIST dataset you have. This is how your MNIST dataset looks if you haven't visualized it in the first assignment itself. So these are your digits. It's a 32 cross 32 or 28. It's 32 cross 32 sized images. Yes. 28? Yeah, 28. Okay, so you don't have to implement PCA yourselves. There are libraries that do it. So sklearn is one of the libraries that you can just import and run your PCA on that. So what this line does here is you're basically selecting the values, the features from the MNIST images. You've picked around what, 1,000 images? Yes, yeah. You just pick your features and then you push it to the PCA.fit transform. Before that, you tell the network, you tell the PCA class how many components that you're trying to reduce the data into. Like you have 784 dimensions, you're trying to project them into 3-dimensional space. So this is what PCA result holds. So here, you can just run it. It is very quick. PCA is super fast. Yeah. So once you run it, you have your values stored in the df object here. So you can try printing what df has. You can see that it is a scalar. Yeah. You see that it is a scalar. So you basically reduce your 784 dimensions into 3 dimensions, and this is your first dimension. You can print 3 dimensions and see all of them are just scalars. So this brings us to another question, right? If you are projecting so many dimensions into a much smaller dimension space, how much variation is it going to capture? It is obvious that you're going to lose some data, but how much data are you going to lose? So in this case, you basically lost. Yeah, so the sum of all of this is what? Less than 25. It's around approximately 25%. So you've lost 75% of the variation in your data. So when you try to compress all of that into such a small dimension space, it's obvious that you're going to lose data. So how can you change this? You can probably increase the size of the dimension space that you're trying to project it into. But we'll see how it'll work. We'll get there in a minute. But before that, let's try to plot and see how this works. So this is your clustering. This is how your MNIST dataset looks when you try to push it in a 3-dimensional space. Does it make sense? Yeah.
Do you need to mean center and
So mean center is basically, yeah, you have to use it for PCA. Yeah. So you don't have to do it right now because the library is doing all of that for you.
because the PC is
Exactly. Yeah. So you have to do that. But that is being done already. You don't have to worry about it. Right now it's, so you can see that the data is not really nice. It's not clustered well. It's all random. You can't really make anything out of it because it's just capturing 25% of the variation of the data that you have. So let's see what happens if you try to project the MNIST data into 50 dimensions. So obviously the results should improve, but how much? So once you run this, you can see that the variance that has been captured in 50 dimensions is almost 83% of the data, 83% of the variance that is in the original data. So this kind of tells us a story, isn't it? So do we actually need 784 pixels? We don't. So why can't we just use a PCA, reduce the dimensions so that you have much faster computation times and you don't have to worry about the training being too slow? It's just one of the things that people do. But there are better methods now. You can use autoencoders and stuff like that. But this is what people initially worked on. So why didn't we start with t-SNE? So basically, t-SNE is very slow. t-SNE is a probabilistic method wherein we saw how each sample is put on a normal distribution curve, and then we compare the distances. So it's a really good method. It's way too slow. So running t-SNE on 784 dimensions is stupidity. Just don't run it. You'll be crashing your computers. So what you can do is reduce the dimensionality, use PCA first, go from 784 to 50, and then you can probably use t-SNE to see the results, at least to visualize it in probably 1 or 2 minutes. So let's try to run this. Okay. As you can see, it takes a while. So you keep running it, and then what's happening internally is each sample is being compared with every other sample in the data set. So it takes a lot of time, but the results are good. Good in the sense it doesn't really help for anything apart from just visualizing that you can cluster things like this. Yeah. And yeah, so once you're done with it, this is how your plot is going to look like. And you can see the difference in PCA and t-SNEs. This is really good. You can humanly cluster different digits. Any questions? It's a really good class. You can cluster it. But the problem is you can't really use this data for anything else but visualization. Any questions with t-SNE and PCA before we move on? Okay. So basically, it's not a linear combination, right? I mean, you're losing all of your data that you have initially. So you're comparing each sample with each other, and you're losing that variation that you would have. And this only works with clustering. You can see how close each sample is with each other. But apart from it, what else can you use it for? And like realistically, you are already removing all of the dimensions by projecting it down with the PCA. If you want to use it in realistic situations where you want to use it on a complete image, for example, most of the images that we have are 4K. 4K is what, 8 million pixels? How would you do it? It will probably take a week to compare 10 samples, I guess. I don't know. Yeah.
When do you know whether t-SNE or PCA works better?
PCA always works better.
PCA
Yeah.
always works better.
Yes.
But in this case,
So this is for human representation. So this works very well to see how clustering works. So t-SNE also works well, but you cannot use it in any realistic situation. PCA is much faster because it's just a line fitting algorithm. You have your samples. You just fit a line, as you can see. So here what you have all of these samples. You start from some random line like this, and you keep turning or changing the slope of this line until the distances between each of these samples is minimum. So it's very easy to fit in a line than comparing each sample with each other. So it's not real. It's not practical. You just can't implement it in real world scenarios. Yes. Okay. So just a quick question. If you try to do a PCA for this class, how would you cluster people? How many clusters would you have? So you are a non-uniform distribution inside this class. You're sitting like this. So if you try to do a PCA here, how would you guys be clustered? How would this end up? How many clusters would you be expecting?
I mean, depends how low the variance is.
I'm sorry? So where is the mean of this class? You'd probably find a mean somewhere there. Yeah, so you find the mean somewhere there. This would be a cluster. That would be a cluster. You would be a cluster. And this whole set would be a cluster. Yeah. So, but these methods are antiquated. You usually never use this these days. You will be learning about encoders soon. So you'll understand why those methods are way faster, way better than what we have, right? And one other thing, what could you guys say about PCA? Right? Do you think linear combination works? I mean, can you just say that, okay, I can linearly combine these variables inside the image? So is that enough? All right. So basically, neural networks help us in this way. You have various levels in which you pick representations at various levels of hierarchy. So that is way better because you cannot judge how the dependencies between pixels are just by looking at one layer of input. You can keep doing it hierarchically, and it's bound to get better results. So coming back. And finally, we'll be talking about ZCA. So till now we spoke about methods where we can reduce the dimensionality of the data, but ZCA is something different. The reason we are speaking about it is it is the first part of your assignment, the second assignment. So ZCA basically helps the network it is a pre-processing step that helps the network focus on areas that are actually important. For example, if you have an image, like this, and you have some interesting object, probably an apple here. So do you actually need to look at the entire image, focus on the entire, all of those pixels to get features out of it? No, right? So ZCA basically helps us focus on the blob in between by just killing all of the other pixels and increasing the contrast or increasing making the features more prominent of the things that actually make a difference. So that's about ZCA. You'll be looking at various other things, like how to use SVDs, what eigenvectors are. I can actually do a brief as well. So basically, these samples that you have, so if you draw a vector like this, and so basically you have to find the difference, right? So this can be represented, the vector that is pointing towards the sample can be represented as a unit vector, which is also called as an eigenvector that you will be deriving in your first part of your next assignment. So that's about it for today. Do you have any questions? Questions? Yeah.
Do you have initializer in PyTorch to initialize the weight matrix and bias?
Yeah, you can use Xavier, which always works the best. Yeah, I think you spoke about Xavier initialization in the last recitation as well.
About the bias matrix, so what's the best way to initialize the bias matrix?
What's the best way to initialize it?
Yeah, like
you can.
it doesn't work.
What you generally do is if you're just randomly initializing, you can maybe initialize it to values between -0.1 to 0.1. But if we really want to initialize it and see how and get the maximum performance, you can just log the values in TensorFlow, see how they're diverging, and then initialize it to that diverge level. But there's no correct way of doing that. But it's always better to uniformly distribute it in a range of -0.1 to 0.1.
That's it. Thank you.